Hey everyone, today we're going to be talking about the concept of differentiability, and as we go through these notes you're going to learn that this concept is linked to the idea of continuity, which we studied a few chapters back, and we'll get into that in a little more later. So we say that a function is differentiable at a particular x value if the derivative of the function exists or is defined at that value of x. Now, we say it's defined if the left-hand derivative is equal to the right-hand derivative. So if you remember back to talking about limits, we always talked about the left-hand limit and the right-hand limit, and so we're going to have the same concept with derivatives, and we'll talk more about that as we get into the notes a little bit here. So in general, functions are differentiable unless one of the following characteristics occurs. So the first thing that's going to make a function not differentiable is if there's any type of, and I'm going to start here, if there's any type of discontinuity. So if there's any discontinuity, so in my example here, I have a discontinuity here, I see I have a jump discontinuity, we would say that our function, and I'm going to assume it's f of x, we would say f of x is not differentiable at x equals 0. And we would say because it's discontinuous. Now, just as a review, when we're talking about discontinuities, it could be a jump, we could have an infinite discontinuity, and we could have a removable discontinuities. Any of those things would make the function not differentiable at a particular x value. And we know we're going to see these types of things. Jump might come from a piecewise, for example. We also know that rational functions could cause these discontinuities to happen. So as soon as we're discontinuous, we know that our function is not going to be differentiable. But let's look at some examples where the function is continuous and we're still not differentiable. In this case here, we have at x equals 0, we have what we call a corner. And hopefully everyone recognizes this comes when we have absolute value functions. Those are going to create these corner points. And I want to talk a little bit about this idea now, about this left-hand derivative and the right-hand derivative. We said those two have to be equal at a given point in order for the derivative to exist. Now, we know when we're talking about derivatives, we're talking about the slope of the tangent. So let's think about slopes with this corner example. If I'm looking here on the left side of x equals 0, so on this piece, I know that's a negative slope. And actually here, if this is absolute value of x, my slope is -1. I know that's hard to see, sorry about that. Now, on the other side, right, I'm actually going to have a positive slope. That's going to be a +1. I'll write over this so you can see it better. So since those two slopes are not the same at this point, that's why we say we're not differentiable, because the derivative isn't going to exist there. Now the next thing we can have happen is this. It almost looks like a corner, except it's not kind of strictly linear at that point. This is called a cusp. Okay, and so again, we see that happening here at x equals 0. And a cusp is going to happen when we have a function with a rational exponent. So it might look like f of x equals x to the 2/3. And again, if we think of this idea of slope, as I'm coming from this side, that's going to have a negative slope. However, the slope on this side is going to be positive. So obviously they don't agree at that point. Now the last thing we can have happen, in this case it's happening again here at x equals 0, we can have what we call a vertical tangent. So if you think about the tangent line there, it's going to be a vertical line, and we know the slope of a vertical line is undefined. So since that slope is undefined, our derivative is not going to be defined at that point. Now this is also going to happen when we have a rational exponent. However, this might be something like f of x equals x to the 1/3. Right here we had an even number in that numerator, so it made our y values positive, but here we've got negative x values as well as positive x values, and in that transition is where we encounter that vertical tangent. So any of these four issues, a corner point, a discontinuity, a cusp, or a vertical tangent, can make our function not differentiable. So we've already been talking about this idea of continuity, and here's one of the big ideas. If a function is differentiable, then it must also be continuous. So as soon as you know a function is differentiable, you also know it's continuous. However, just because a function is continuous does not necessarily mean that it's differentiable. Right? And we saw that in 3 of the examples above. For example, this function where I had my cusp, it's continuous. I could draw that function without lifting my pen from the page. However, because of the cusp, it's not differentiable. So let's go ahead and look at some of the problems that we could encounter dealing with differentiability. And just like we've kind of always done, we're going to start just by looking at a graph. So you might get something that looks like this. We have a graph, and you're just going to be asked to identify the x values where the function's not differentiable, and then explain why it's not differentiable. So which of those 4 things that we identified are happening at that particular point. So the first thing that I notice here as I'm looking is I have a discontinuity here at x equals -2. So I have a discontinuity, and I'm just going to specify here for review purposes, we have an infinite discontinuity. There's a vertical asymptote there. So that's the first place where my function is not differentiable. Now, as I work my way over, I notice this here at x equals -1. That's going to be a cusp. So I'm not going to be differentiable there. Next thing I see here is at x equals 0. I have a vertical tangent at that point. And then the last thing is here at x equals 2. I have another discontinuity. And this time that we would classify as a removable discontinuity. So that's kind of part 1, is if I have a graph, can you identify where the function is not differentiable? Now, the second part is to look at a function and determine whether or not it's differentiable. So in number 2, I have a piecewise defined function, and in part A, they're asking me whether or not the function is continuous. So remember, to prove that a function is continuous, we had to first show that the two-sided limit exists. So in other words, for this case, the limit as x approaches 0 from the left of f of x is equal to the limit as x approaches 0 from the right of f of x. And then to be continuous, it also has to be equal to the function value at that point. So at this case, when x equals 0. So let's go ahead and take a look. 0 from the left is going to be defined by my first piece of the function. So if I plug 0 in, that's our first kind of rule of trying to find a limit. If I plug 0 in, I get 0 from the left side limit. From the right side, again, I'm going to plug 0 in. So I'm just going to specify here, this came from plugging 0 into 0 squared. On the right side, I have 2 times 0, which is also going to give me 0. And my function value is also going to be 0. So since those 3 values are all equal, we would say that f of x is continuous at x equals 0. Now, the next part is going to ask us whether or not it's differentiable. We said to be differentiable, the derivative has to exist, which means the left-hand derivative is equal to the right-hand derivative. That's what we're checking for. So for the left side here, my function is x squared, which means my derivative is 2x. So if I plug in 0, I get 2 times 0 is equal to 0. So my left-hand derivative is equal to 0. Now for the right side, the derivative of 2x is just 2. So anywhere along that piece, I'm going to have a slope of 2, which makes sense since this is linear. Since 0 is not equal to 2, we would say that f of x is not differentiable. At x equals 2. So that's kind of the algebraic process. Now I just like to kind of revisit the graphical piece for a minute. So I'm just going to sketch a graph here of what's going on. So for x less than or equal to 0, I'm defined by x squared. So I know I look something like this. For x greater than 0, I'm defined by 2x. So it looks like this. So I've kind of got this, it's kind of a cross between, I guess, a corner and a cusp there. But again, those slopes are not going to match at x equals 0, so we know we're not differentiable. The graph just kind of confirms what we found out with our calculus and algebra. All right. We will go ahead and skip number 3 for now. We'll revisit that in class if we need it. Let's look at number 4, and this is a good example of what this might look like on an AP test. So it gives us f as a piecewise defined function, and they tell us that c and d are constants. It's telling us that f is differentiable at x equals 2, and then we need to use that information to find the value of c plus d, the sum of those two constants. So let's use what we know. We know that if it's differentiable, that means that the left-hand derivative must equal the right-hand derivative. So let's see if that's going to help us out. I'm going to make my table like I did before. And I've got the right-hand derivative. So let's see, my left side here, I know c and d are constants. So the derivative of cx, that derivative is just going to be c. Since d is a constant, that derivative is going to be 0. So that's going to cancel. So my left-hand derivative is just equal to c. On the right-hand side, my derivative is going to be, well, x squared, that derivative is going to be 2x. And then minus cx, that derivative is just going to be minus c for that term. So now c is a constant, and I don't know the value of that, so I'm just going to leave that as c. For this one, I know I'm looking when x equals 2, so I'm going to plug in 2 for x. So I've got 2 times 2 minus c, or 4 minus c. Since this is differentiable, I know these two quantities have to be equal to each other, so I get the equation c equals 4 minus c. If I add c to both sides, I get 2c is equal to 4, and then I know c is equal to 2. Now, I'm not done because I was asked to find the sum of c plus d. So let's go back here. I need to find the value of d. Okay, so here's where we're going to have to go back. Now, I started here because I knew those derivatives were equal to each other. So now I'm going to use this idea of continuity as well. I also know, let's see, that since this is continuous, my left-sided limit is going to be equal to my right-sided limit. So let's see if this helps us, because right now I don't have a way to go back and find my value of d. So we started here, and then we also said, well, if f is differentiable, we also know that f is going to be continuous. So let's see if looking at this helps us. My limit as x approaches 2 from the left is going to be, let's see, 2c, because I'm going to plug it in, 2c plus d. My limit as I approach from the right, if I plug 2 in, is going to be, let's see, 4 minus 2c. So now I have the equation 2c plus d equals 4 minus 2c. However, I can take my c equals 2 and I'm going to plug it in to my equation. So I know 2 times 2 is going to give me 4 plus d is equal to, well, 2 times 2 is 4 and 4 minus 4 is 0, so d must be equal to negative 4. So now for c plus d, I have 2 plus a negative 4, and that value is going to be negative 2, so choice B. So a lot of times these types of questions are going to ask you to make connections between differentiability and continuity in order to solve these problems. All right, that's it for this video. See you when we're back in class. Thanks.